Okay, so let's go back to this very quickly again. 6 one. An organic compound, solvent, and water. Sorry for that. An organic solvent and water are immiscible and form biphasic system. Partition coefficient of the X between organic and water is given as this one. An amount of 50.4 moles of X was added to a system containing 100 cubic centimeter of organic and water. So basically, if I draw here very close to this one, okay. So this is 100. This is 100 cubic centimeter. Okay, so you add 0.5 moles of X. Okay, you add 0.5 moles of X. And yeah, sorry again. Was allowed to reach equilibrium at temperature T. So temperature T, it is given. Calculate the concentration of X in organic and X in water. So basically, the distribution coefficient is given as 4, right? So distribution coefficient means X in organic, X in aqueous. So the only thing that we know here is the total amount of X, that is 0.5 moles. So if I take this Kd equal the moles of X present in organic as to be, let's say, Y moles, and the lower amount will be 0.5 minus Y. Why? Because the total amount is 0.5. So if I write in terms of concentration, it would be Y divided by 100 into 10 to the power minus 3. 0.5 minus Y would be 100 into 10 to the power minus 3. So automatically this volume to volume cancel, because that is why we can directly use the amount of moles, because the volumes are same, organic and aqueous. So here 4 will be equal to Y over 0.5 minus Y. So you can find Y here from this. So basically it is 2 minus 4Y is equal to 5Y. 5Y is equal to 2. So Y is equal to 2 divided by 5. So it is 2 divided by 5 means 0.4 moles. Okay. So this gives the idea in the organic phase there will be 0.4 moles. Right? In the aqueous phase, there will be 0.1 mole. That's the idea. This is a simple idea. So that is total 0.5 moles. So to calculate the concentration in organic, so basically 0.4 mole divided by 100 into 10 to the power minus 3. Okay. So you can find the concentration using this one. Concentration of X in water, 0.1 mole divided by 100 into 10 to the power minus 3. Okay, so these are very straightforward things, right? You can easily find the values here. Right, so this would give you 4m, this would give you 1m, typically. That's it. Let's go back to the part B. The compound Y is soluble only in aqueous phase, right? So they say this is soluble only in aqueous phase. And in the aqueous phase, X and Y react to form Z. The presence of Y does not affect the distribution of X between organic and water. So basically, you know here, so this is our organic, this is our aqueous, And here there is X that is distributed like this. If I imagine, so when you add Y to this solution, this reaction, Z is going to happen. That means Z is formed. And they say the presence of Z and Y does not affect this distribution. That means they say the KD between X organic over X aqueous still going to remain at 4.0. No problem at that temperature, particular temperature. Okay. A series of biphasic system containing organic water was prepared. Then different amounts of X were distributed in the biphasic system and the systems were allowed to reach equilibrium. The initial rate of the reaction between X and Y in the aqueous phase was measured after adding Y into the system. So you have this one, then what they add? They add Y, then this reaction is going to happen. Results of this experiment conducted at temperature T given in the table. So this is the way. So they have used 3 different systems. So I will draw this 3 different system here. So this is 1, this is 2, and this is 3, right? So here they have used different volumes. So for the first one, volume of organic is 100. This is also 100. Here the second one also 100 and 100. Okay, so let's say this is organic on top, aqueous in bottom. So the third one, 50 and 50. Okay. The total amount of X added moles. So basically what they have done is they have added 0.05 moles of X here. So let's say that is X is added here in this place here, X 0.05, and here that is 0.1 mole of X. This is 0.05, and here the amount of X is 0.25 moles of X. And then what they have done is they have added Y. So how much Y they have added? We have to calculate that one here. Y is given. You don't have to calculate 0.02, and here Y is 0.04. and here Y is 0.02 again. So very nice. So these are the 3 systems, and they have found the initial rate also. This is 2 into 10 to the power minus 6, and here 1.6 into 10 to the power minus 5, and here 4 into 10 to the power minus 4. Right. So these are the things that they have given. And we have included all the things in this picture. So give me a second again. Okay, given that the concentration of XY in the aqueous phase and aqueous phase, write the expression for the rate. So automatically our rate will be equal to rate constant K times the concentration of X in the aqueous phase. The order is given as M and N, so I would write this M, and Y concentration aqueous, and the order is N. So this would be the rate equation. Calculate the initial concentration of X in the aqueous phase in each experiments. So this is the point that you should be aware of. Okay, this is the place where student made mistake. So here initially you have 0.05 moles of X, that is the total amount of X added here in the aqueous phase. So some student calculate the concentration, initial concentration of X in different ways. So you need to think whether I use this 0.05, all 0.05, and then divide it by the volume of the aqueous phase, 10 into 10, 100 into 10 to the power minus 3 to get the concentration. Or I need to first find the amount of X remaining in the aqueous phase and then use the remaining amount to calculate the initial concentration. Okay, that was the thing that you need to check. So in the statement C, it is given clearly the biphasic system were allowed to reach equilibrium, and then the initial rate of the reaction between X and Y was measured after adding Y. So if they ask the initial concentration to find the rate, it is always after the equilibrium that they have added an amount of Y to initiate this particular reaction. Okay, so first they have allowed to equilibrate, then they add Y. So the initial concentration means for this particular reaction, that is the amount of X remain in the aqueous phase after this physical equilibrium happen. So you need to first find how much X is remained here in the aqueous phase using this distribution coefficient value. So basically it would be like, since the volumes are all equal here, again you can write down a statement, since the volume are equal, for the KD expression I can use the amount of moles. So what you can do here is you can use here like 4 equal, if you think the amount of moles in the organic phase here to be Y1, here it would be Y2, and here it would be Y3, you can directly write down 4 is equal to Y1 over 0.05 minus Y1. And here 4 is equal to Y2 over 0.1 minus Y2. And here 4 equals Y3 over 0.25 minus Y3. Then you can find Y, and then you can subtract Y from the total amount 0.01. Here you can subtract Y2, which is the amount of organic in this one, and find the amount here. Or otherwise you can take in the aqueous phase as Y1, then you can automatically write here 0.05 minus Y1, Y1. So when you find Y1, it is the amount present in the aqueous phase. I mean, if you think the amount of remaining in the aqueous phase is Y1. Now here what I have done is the amount remaining in the organic is Y1 I have taken. It is your wish, you can take in either way. Then you can find the concentration in this one, initial concentration based on the amount divided by the total volume. So if I find the amount, the concentration in each of these experiments, you will find that this is 0.1 m. This is 0.2 m. And in here, in this sample, in this test, it will be 1 m. Okay, that is this. So what is the point to remember? Initial concentration means not the total amount. After the equilibration, what is the initial concentration? Calculate the initial concentration of Y. So calculating the concentration of Y is not a problem here. You don't have to think much because Y added amount is given directly. So you can find the concentration of Y quickly. So here the concentration can be automatically found. So the only thing that you have to do here is divide 0.02 by 100 into 10 to the power minus 2. So you will get the values 0.2. Here it will be 0.4 here because it is twice. And here it is lower, but volume is different. So it will be 0.4 here. And so these are the concentration that I have here. Calculate the orders m and n of the reaction with respect to x, y respectively. So how can I find that one? So it is not a big thing. It's not a big deal because this reaction, for this each test, now you know what could be the rate equation. That's the idea, okay? Because our rate expression is this one. So based on that, for the first test, I can write down 2 into 10 to the power minus 6. So write everything including the units should be equal to rate constant time concentration of x. Okay, so this is concentration of x, not A. Sorry, yeah. So concentration of x. What is the concentration of x? 0.1 m to the power x. No, yeah, to the power m. And then what is the concentration of y here? 0.2 m to the power n. So this is my one equation. In the similar way, you can write down equation to this one. So this would be 1.6 something equals rate constant time. Again, you know the concentration 0.2 m to the power m, and then again 0.2 m to the power n. So this will be my second equation. Okay. Okay, so this is 1.6 into 10 to the power minus 5. Then the rate, third rate, 4 into 10 to the power minus 4 is also equal to 1 m into m, 1 m into m, and 0.4 m into n. So I have 3 equations, very nice 3 equations now. Okay, this is 1 m. Okay, 1 m. Now what you have to do, same way in all other previous questions, that you need to just find m and n by dividing two equation. For an example, if you divide one first equation by the second equation, you will see this one and this one is going to cancel out. You can automatically find m. Okay, so 1 divided by 2 will give 0.02, 0.04 equals. So if I divide 1 by 2, this will give 0.04 equals what is it? 1 over 2 means, yeah, 1 over 2. Yeah, so basically it would give 0.04 times 0.2 to the power m, right? Power m. So basically 0.2 times 0.2 means 0.04, right? So m would be equal to 2, right? So here we will find m is equal to 2, and do the same for n. Find n, you will find n is equal to 1. So that's the idea, right? You divide 3 by 1, you can get n is equal to 1. Then they say calculate the rate constant. So when you find m and n, so plug here for the first equation or second or third, then you can find k. That is easy, right? So the only difficulty in this equation is the identification here. The initial concentration of x is after the equilibrium, and all other things are very, very easy, right? And I like this question because, sorry, they try to combine the chemical kinetics to a physical equilibrium, like the phase equilibriums. Okay, so very nice. Let's move on to the next part. An experiment is designed to study the effect of the temperature on the reaction rate using the partition coefficient given below. Okay, so an experiment is designed to check the temperature effect for this particular reaction. Is this suitable experiment to study the effect of the temperature on the rate of the reaction? Explain your answer. So one important thing is, when you increase the temperature, you know it will definitely affect this reaction, x plus y giving z. There is no point, no problem in that. Okay, it will definitely affect. So you can study. But the problem is, when you increase the temperature, there is another effect that is going to come. That is this partition coefficient, distribution coefficient, because it is also an equilibrium constant. So when you change the temperature, it will also change. So there are two things here that is changing. One is the partition coefficient. Another one is this rate constant. So when you increase or decrease, or when you change the temperature, there are two things that is changing. One is the rate constant, the other one is the partition coefficient. So you can't use here. You can't. This is not a suitable experiment because KD affects on temperature. So it will also change. Okay, you can explain in that very simple way. Right, part C. The organic solvent, organic to water was also immiscible. So this is another simple question. So again, I will take this as organic, and this is aqueous. 0.2 mole was added to the system containing 100 cubic centimeters. So this is again 100. This is also again 100 cubic centimeter. So they have added 0.2 moles of X here. And they have allowed to keep this like in equilibrium. So X will be distributed among the organic 2 and aqueous phase. Then they say Y is added. So again, this particular reaction is going to happen, X plus Y giving Z. Now we know the rate expression, K times concentration of X to the power 2 and concentration of Y to the power 1, because orders are not going to change when the concentration is changed. Okay. And the initial rate was measured, and Y does not dissolve in organic 2, so no problem. And the initial rate is also given. So this rate we know, 6.4 10 to the power 7. Put the unit. So they are telling calculate the partition coefficient of X organic aqueous over distribution. Okay, that's it. You have to find the KD factor here. So new KD in between organic and aqueous. So first point here. Okay, the only thing that we know is initially added X number of moles, that is 0.2. Okay, so we know the total X, that is 0.2 moles. So in order to find this KD, we need to know the amount of X present in the organic phase as well as in the aqueous phase after equilibration. But the advantage is we can find the initial concentration, such as here, you can find the initial concentration after the equilibration, which means the concentration of X in the aqueous phase, by using the rate expression, right? So rate is this. What is the rate constant? So rate constant we found here in the previous question, 5. So you find the rate constant. In fact, if I check the rate constant, it is 1 into 10 to the power minus 3. So here it will be 1 into 10 to the power minus 3. So do you know the initial concentration just after the equilibration for this reaction? No. So you just take this as X squared. But you know the concentration of Y. So Y is 0.01 divided by 100 into 10 to the power minus 3. So basically Y is 0.1, right? So this is 0.1. Put the units. From this, you can find the concentration of X. So when you find the concentration of X, you will get it is 8 into 10 to the power minus 2. So it is 0.02 M, 0.08 M. And if you know the initial concentration of X here, which means here in the organic phase, X organic, and then X aqueous. That is what you need to put to find things. So you know the total moles of X, that is 0 0.2. So how can you find the X aqueous, let's say moles for an example? So moles means CV, concentration time volume. So concentration is known 0.08, and volume you can find, this is 100. So 100 into 10 to the power minus 3 to calculate the amount of moles. Okay. So this mole is, what is it? Multiplied by, 8 into 10 to the power minus 3. That is in aqueous. So what is the amount in organic? In organic, it will be 0.2 moles minus 8 into 10 to the power minus 3 moles. So basically, if I write in the 10 to the power factor here, it will be 200 10 to the power minus 3 minus 8 into 10 to the power minus 3. So it will be 192 times 10 to the power minus 3 mole. Then what you can do, organic moles, you know, now the concentration is 192 10 to the power minus 3 over volume is 100 in both cases. So I can divide it directly by the number of moles over 8 into 10 to the power minus 3. So minus 3 to minus 3 will cut. So 192 divided by 8 is 24. Give me a second again. Right. So this is how you can find easily. This is the idea. So this is also a nice part, because here you need to calculate the rate constant, and here you need to use that rate constant to get the concentration of X initial. Then you can find the equilibrium amount present in the organic phase. Then you can divide these two to get the distribution coefficient. Okay. Yeah, so that is it. That is also a very nice question.